And now I'm going to talk about the Naïve Bayes Gaussian classifier. So often we'll have data sets which aren't just single values, and we have to build classifiers which classify data with vectors rather than single measurements as our inputs. We know that the one-dimensional Gaussian function has the corresponding formula that I'm going to show here. So the probability of data point xi given the model B is given by 1 divided by the square root of 2 pi sigma b squared, and then we multiply that with the exponential function, which is then raised to minus xi minus mu b squared divided by 2 sigma b squared, where all the values here are now scalars, right? They're all one-dimensional values. Now, in the multi-dimensional case, of course, the data is now a vector, so we have xi with a hat on it, just in this case representing the fact that this is actually a vector. And the main difference is, well, basically we instead of having sigma squared as the variance, we now have this capital sigma, and which called in this case capital sigma, which is now the covariance matrix of this case of the data for C. And in the exponential, rather than having just single data points, now we have the vector xi take away the mean vector transpose multiplied by the inverse covariance matrix, again multiplied by the data vector take away the mean vector. In order to use this model, of course, then if we wanted to build a classifier based on the multidimensional Gaussian, we'd need to know what the mean vector was and the covariance matrix was. Now, the probability of a data point, how probable the data is under source C, is then given by this expression. That's basically what it's telling us, right? It's telling us, given the model C, what's the probability of the data vector. And we can rearrange that, because what we actually want to do when we want to do classification, we want to know what the probability of the data is that came from C. Right? We want to know what's the probability that we have class C given the data. And what we can do is we can rearrange the form of this conditional probability from probability of x given C into probability of C given x if you use Bayes' rule. And that's what we've done here. So probability of C given x is now probability of x given C multiplied by the probability of C divided by basically the probability of x, which we're actually doing by now marginalising out over this expression here, just like we did before. Again, most of the time you can actually ignore this expression, because when you're doing your comparisons of which class it came from, it's the same term in the denominator of all of them, so we don't necessarily need to calculate it. So what we need to do with a classifier then, if we'd have one of these expressions for each class, and we just, in a naive way, we just choose basically the probability for the class given the data which was highest. Now, the problem with using a full Gaussian is we need a covariance matrix, but actually trying to estimate a covariance matrix is a bit of an issue. So why could this be? Well, if you think about it, if we have a data set of one-dimensional data, let's say we need 1,000 samples to estimate the variance to a reasonable extent. That's just off the top of my head figure as an example. So what about the covariance? Well, you think about what the covariance is saying is it's now the variance is just comparing the data with itself. The covariance is how one feature actually relates to another feature. So if you think about it, in order to get a representative set of one feature, let's say, like I said, you need 1,000 samples. To get a representative set of how one feature differs from another feature, you need to have a represented set of all the ways these two things can be different. So rather than maybe needing 1,000 samples, you'll need 1,000 times 1,000 in a two-dimensional case. So you need a lot more data in order to be able to do a reasonably good job of estimating covariance than you do estimating variance. And that becomes a gigantic problem with really, really high dimensional spaces, because you'll need a huge amount of data. So basically we can only estimate the covariance effectively then if we've got a reasonable amount of data and we get occurrences of how things co-vary. And generally speaking, we never will see in the data how everything really effectively co-varies together, right? So that's just an example there. So what's the solution? Well, if we can assume that the features are independent, then all we have to care about is what the variances of the features are. So what's the sigma squared for each feature? And we'll just forget about covariance. So if we assume things are conditionally independent, and that means given the class, we're going to assume the feature is independent, then that's quite nice. Then basically what happens is the covariance terms all go to 0, and then rather than having this this covariance effect, what we can do is assume that the overall joint probability representing this high dimensional probability space is actually then just the product of the individual distributions for each feature, right? So it's just a product of the individual ones rather than having to have this complicated covariance term. So if we can actually, if we make that assumption that we're going to assume that all the features are independent, that's nice, because then all we have to do is calculate the probabilities of each feature independently and multiply them together in order to get the overall joint probability. So if we had two training data sets, one for A and one for class B, and let's imagine we've got two features. Well, all we have to do first of all, we need to calculate the means of each feature. So we calculate the mean of feature 1 in data set A, which is just basically the sum of the values of that feature divided by how many times they actually occurred. Same thing again for feature 2. All we have to do is look at feature 2, calculate its mean value, which is by summing up all its values and divided by the number of times they occurred. And then we have to calculate the variance of class A feature 1. So we just look at that one-dimensional value again and we calculate the variance. So it's going to be basically the data value for feature 1, take away its mean squared plus, and so on across all the times, and we get samples there divided by the number of times take away 1, because we want an unbiased estimator. And again, the variance for feature 2, we just look at feature 2 and take away its mean and square it and add up all the values and divide by the total number of occurrences minus 1, right? So we've got a relatively easy thing to do, calculating these variances and these means just by looking at individual one-dimensional values. And then, of course, we've got to do the same thing for class B. So we end up, after we've done that, we'll end up for class A, we'll end up with a mean vector, in this case, because it's two-dimensional, a mean vector with mean for feature 1, mean for feature 2, and for class B, corresponding mean to feature 1 and mean for feature 2. And we'll end up with our corresponding covariance matrices. Our covariance matrix for feature A is going to be, sorry, not for class A, is going to be the variance for feature 1, a 0 covariance term here, a 0 covariance term here, and another variance term for feature 2 here. And the same thing basically for the covariance matrix for class B. Again, we've only got variance terms in this matrix, and the covariance terms are set to 0. Right? That is the naive Bayes assumption. We assume covariance is 0. So what does that mean, right? Well, now we can calculate the probability again of getting data from class B. In this case, if it's a Gaussian, we just have to look at the single dimensional case. If we got two features, then a single pattern is going to have the following mean. Sorry, the following form two-dimensional data, where D1 and D2 represent dimensions 1 and 2. So, because we're assuming now that the features are independent, the joint probability distribution of the two features is just given by multiplying them together, because we're assuming that they're independent. we don't have to evaluate things fully using the covariance matrix because we don't need the covariance terms. So now they're independent, we just calculate the probability of the data comes from B for feature 1 and the probability of data comes from B for feature 2, and we multiply them together. Then we've got the joint probability distribution. So that's what we're going to do. We're now just going to plug in basically the formulas for the Gaussian, which is giving us this x di given b and x, d1 given b and p x d2 given b. That's the first expression is for the first Gaussian, and the second expression is for the second Gaussian. We multiply those together. And this is just listing what these values actually are. So obviously these are the data points for dimensions 1 and 2. These are the features 1 and 2 mean values, and these are basically the standard deviations as well, right? So that's what we need to calculate. This is what we're after. Now this is now the overall vector. The probability of the x data vector given b is given by the joint distribution that's given by this expression of 2 multiplied Gaussians, right? Now what we have to do is, that's fine, we've got the data given the model. We need the model given the data because we need to decide on which class it's coming from. So given the data, we want to know which model probability is bigger. So what we do is we use Bayes' rule again. We have to calculate this term. Again, like I said, the denominators here are the same in both cases. So generally speaking, they can be ignored when we're making comparisons between these. Right, so that's what we do. We're going to calculate all of these things. If probability of A given X is greater than probability of B given X, then it looks like the data is more likely to come from class A than class B, and vice versa. So let's look at Naïve Bayes, what it's saying. Well, basically then what it's saying is, because we're assuming the features are independent, the joint distribution across the entire data vector given the class is going to be approximated by the product of the distributions for each feature with each feature. So we basically just multiply the distributions for each feature together rather than having to use this big Gaussian formula. And the full Gaussian formula, this is a shorthand version of it, but the full Gaussian formula would involve us actually calculating using the full mean vector and the full covariance matrix. Now, Naïve Bayes does obviously assume independent features, and data is not always independent. It's called Bayes classifier. It's not necessarily a Bayesian method as such. Bayesian means you're using Bayesian inference and stuff like that. So it's just, that's not always the case. It is a simple supervised learning method. There are definitely better methods out there. It's a nice way of putting a few things together. What makes us, it's not necessarily a very effective method compared to neural networks, for example, but it's a good, interesting way of looking at things. We have to, of course, incorporate priors on the parameters, and if let's say we're unlucky and we just get a count going to 0, then we have to do something about that. So sometimes we have to, you'll probably people hacking these things and putting small little tiny epsilon values in, so things never actually go to 0. Another thing which can happen is sometimes what's going to happen is that what you're actually trying to model isn't actually a Gaussian, in which case you might have to use a mixture of Gaussians rather than a single Gaussian. So basically it's only basically guaranteed to work if the probability distributions really are Gaussian, if we can effectively estimate what the parameters are, even though we're using this Naïve Bayes approximation, which makes it easier. We use the appropriate prior, but it's more of a, I think conceptually it's quite a nice thing to understand how to do, and it introduces lots of concepts in machine learning together, and uses Gaussian distributions.